Welcome to Pomodoro Joe for Monday, April 24th, 2023. Today we're looking at LeetCode problem 1046, last stone weight. This is an easy problem. You are given an array of integers, stones, where stone's index I is the weight of the ith stone. We are playing a game with the stones. On each turn, we choose the heaviest two stones and smash them together. Suppose the heaviest two stones have weights x and y, with x less than or equal to y. The result of the smash is, if x is equal to y, both stones are destroyed. And if x is not equal to y, the stone of weight x is destroyed, and the stone of weight y has a new weight of y minus x. At the end of the game, there is at most one stone left. Return the weight of the last remaining stone. If there are no stones left, return 0. Okay. They're only up to 30 stones, that's not too bad. And then the stones can weigh between 1 and 1,000. All right, so we'll put 25 minutes on the Pomodoro timer and we will get started. So this one seems pretty straightforward actually. We'll just do exactly what they tell us to do. And in fact, we'll go recursive on this. So the idea here is we will take the heaviest two stones, smash them together, and whatever remains of our stones, we'll do the same algorithm again. So we will recurse. All right, so with a recursive function, the first thing we always do is write our base cases. Now, what are the base cases? The base cases are the cases in which you won't do a recursive call. It's when you're done processing and you can just return. So in our case, we have, I see maybe two base cases. So one base case is we have no stones left. So let's just do that one first. If not stones. So if there are no stones left, then we return 0. All right, so we ran out of stones, we return 0. The other option is there's one stone left. Now, if there's just one stone left, well, then we return the weight of that stone. Okay, so that takes care of our base cases. We don't have any stones or we have one stone. Now we have the case where we have many stones and we need to find the two heaviest stones. So the simplest way to do that is just to sort our stones. So I'll create some new variable here. All right, so I have a new variable, sorted stones, and it's just the sorted version of our stones. Now, this sorted function takes in an array and returns a new array. So it's not modifying this array in place. It is creating a new array and returning it, and we're storing it in sorted stones. Now our two heaviest stones will be at the end of the array because it's a minimum to a maximum sort. So the minimum values will be at the beginning and the maximum values will be at the end. Now we're going to take advantage of something that Python offers, which is a way to index at the end of the array, and that's using negative indices. So if we want to get the last stone or the heaviest stone in our sorted stones, that's going to be sorted stones at -1. Now, not all languages offer this functionality. Sometimes you'll have to call a different function like get last or just last, or you'll have to get the length of our sorted stones and then index at that length. But in Python, we can use -1, so we're going to use that. So this is going to be the heaviest stone. So at this point, we have a couple different options. We have at least 2 stones, because we know we have more than 0 and more than 1, so we have at least 2 stones. Now we need to compare the second heaviest stone to the heaviest stone, or the 2 heaviest stones. So that's going to be stones at -1 and stones at -2. So let's see, we'll just compare these. Okay, so we'll compare the heaviest stone, that's stones -1, to the second heaviest stone, which is stones -2. And if they weigh the same, then they're both destroyed and we move on. So now we can recurse. So we'll just return our last stone weight. Now we'll pass in our new sorted stones without these last 2 stones because these 2 stones were destroyed. So our new sorted stones, actually I'll break this out, we can optimize later. So our new sorted stones will just be the sorted stones, but will only go up to and not include the last 2 stones. So this is another feature of Python that not all languages will offer. In Python, you can do something called slicing, but basically we can take our list here, or our array, and we can slice it and just keep part of it. So we're going to keep the beginning, so that's technically 0 up to, but not including, the -2 indices stone. So basically this will just take us from 0 to the second to last stone, but not include that second to last stone. So we're just eliminating, let me phrase this differently. We are eliminating the last 2 stones from our sorted stones array, and we're creating this new array, new sorted stones that don't include those last 2 stones. So we'll just put that in our recursive call here. And that takes care of one recursive case. So the second recursive case is if our heaviest stone is heavier than our next heaviest stone. Well, then we have this other condition here where we basically have to destroy the second heaviest stone and then reduce the heaviest stone's weight by that amount. So let's see, if we've passed this section where they're not equal, then we already know that the heaviest one must be heavier than the second heaviest one. So we can do something like this. We can say new heaviest, or we'll call it new stone weight. How about that? So we'll just take the heaviest stone and we'll subtract the second heaviest stone's weight, and that gives us our new heaviest stone's weight, or our heaviest stone's new weight. So this won't necessarily be the heaviest weight anymore. In fact, it probably won't be. But now we need to do the same thing here, where we have a new sorted stones, but we have to remove the 2 heaviest stones. We've smashed them together, and now we need to add back this new stone weight. So we can just say plus, and we have to wrap it in a list, so we can do an append, the new stone weight. And then we'll do our recurse again, but this time we'll just pass in the new sorted stones, which is a different new sorted stones than this one. Okay, so I think this should do it. This is our base case. If we don't have any stones left, we return 0. If we have 1 stone left, we'll return that stone's weight. Otherwise, we'll sort all of our stones, and then we'll check, is the heaviest stone the same weight as the next heaviest stone? If it is, then we'll destroy both of those stones, throw them away. We have a new sorted stones, which removes these last 2 heaviest stones, and then we'll call recurse on the new stones. So we basically throw out those top 2 stones, and we try again. All right, so if the 2 heaviest stones are not the same weight, then we know that the heaviest stone must weigh more than the next heaviest stone. So we find that new stone's weight, we remove our 2 heaviest stones, and then we put this remaining stone back onto our list here. And then we'll call the recurse. And the recurse will sort them, so we don't need to worry about this being in the right place. Okay, so this should do it. Let's see how we do. And we pass. Let's submit that. And we pass. We beat 45% for runtime and 47% for memory. Not too bad. Let's see if we can clean this up a little bit and make it a little faster. So I did a bunch of refactoring here to try to get a better score. Nothing really worked all that well, so I won't bore you with it. But I will leave you with a little bit of a teaser in case you want to try something different. All right, we're running low on time, and I don't think I'm going to get it any better than our, what did I get, 70%? So that's the best one we got so far. Now, I think the most expensive piece of this algorithm is this sort, because we're sorting multiple times. If you want to make this go faster, you could probably just sort once. Then when you remove stones and you replace the stone with this new weight, you can actually just find the insertion point and insert it at the right point, keeping everything else sorted along the way. So you can do that using something like a heap. There's a min heap, but there's no max heap. So you might have to do some playing around with the heap data structure to get this to work the way you want. Typically what you'll do is you'll multiply the weights by a -1. So you store everything as a negative value, which means that the heaviest values will rise to the top because they are the minimal values. They'll be the greatest negative values. Okay, but that's it for me. Hope you enjoyed this, hope you had fun, hope you learned something, hope you can go out and write better code.